Okay, so I guess it's time to start. Good morning. Okay, so today we are going to talk about time trigger architecture, and this one is an architecture that is taking more and more place in industry today, and is an interesting discussion because you heard a lot about synchronous model computation. So we talk about how to do synchronous in as model of computation. We talk about the software aspect of synchrony. And today we are going to talk about the architecture of a distributed system using this concept. Now, the important thing is that if you look at the evolution of embedded system, we are going towards more and more safety-critical system. And so that's a great interest in synchronous architecture and synchronous everything, right? Because that eliminates a lot of the problems that we normally have when we use an event trigger model, which is, for many, the most natural way of encoding and representing things. Now, in this particular segment of the class, I wanted to show you what are then all the intricacies and issues that you need to resolve when you want to implement that model into reality, into physics. Right? So we have seen that in the case of electronic circuit design, the mechanism of implementing synchrony is the registers and the clock. Right? And so everything kind of moves, the computation moves from left to right, so to speak, across combinational logic. Then you write the register, and then the clock comes in, you transfer data into the output buffer, and then you read the data. So this guarantees the fact that you have no races, right? As long as the computation is within the clock cycle. So now this is rather simple, if you like, and it is a very well-known mechanism. Everybody plus his brother uses it. So then later on in the history of design, this mechanism was transported into software and then last but not least, into the architecture of distributed systems. So today we are going to talk about that. And I wanted also to project what is the frontier of industrial development in this domain, right? And so we will see that the next generation situation will be an attempt of combining the event-driven and the time-triggered or synchronous model. So these are, I ransacked slides right and left because this one is a topic that has been presented under many different angles, and so I try to synthesize what is known in a unified presentation with slides from everybody plus his brother. Okay. So first of all, what happens in today's system? So if you open up a car today, you find more than 80 processors that are connected together and perform different tasks. Information systems is all what goes around and tells you what is happening. The sensors telling you what is happening in the car. The body electronics is talking about air conditioning, theft warning, opening and closing the door. The module that is taking care of the lights. And then there is the body electronics, which is typically the safety-critical part of the system. So now, interestingly enough, for every one of these functions, the connectivity of the components that do that calculation is given by different wires and different protocols. So it's a real mess. It's an ugly mess. Now, this one is the actual car architecture. So I took away the names because it's confidential information, but it's a real car that is running today on your road, right? And so the name of the maker and the name of the car will remain unknown, and the name of the various functions have been carefully erased, otherwise you will find me in jail next month or so I will not be able to grade your papers, but that's what it looks like, right? And so you have all these different boxes, and each box is a piece of hardware, right? And the connectivity are buses that float around. So in a car today, there are something like, you wouldn't believe this, but how many meters of cables do you think are in a car? how many? I already asked the question. Damn. Okay, so there are lots of wires, right? 10 kilometers of wires, right? Some for with large cars, there are 10 kilometers of wires, and the weight is correspondingly. So this is a mess. That's the reason why you have so many. So now the point is that these nodes are sensors, of course. There are compute elements, and there are actuators, right? Now the point is that the sensor collects data, and they send to the compute element. Compute element does computation, then actuates the actuators, right? Now, the key point is that you want that to happen in a correct fashion, right? And so the key issue is that how are you going to guarantee that? Now, the other thing is that when you look at that architecture I showed you before, there are different companies that are doing different things. So the OEM, so the BMW of this world, the General Motors of this world, take care of the car in its totality. So they do what is called system integration. So they integrate various parts. The tier 1 suppliers, like Bosch and Delphi and so on, make the boxes, okay, that you saw in the previous architecture, right? And so the point is that, and then below, inside the boxes, there are tier 2 suppliers that are, for example, the semiconductor makers. So the flow of information and of design is quite complicated. Now, the issue here is that if you want a very clean supply chain, you want the people who do the components to be able to design their components in a clean fashion. So they just have requirements, they design to that requirements, forget about it. The system integrators would like to take all these components, plug them together, and hope that everything works. Now, that is a very big if, right? So that is some of the issues that we need to worry about. Now, this one is a rolling mill, so it's paper-making machines, right? And so it's not that different in terms of the global architecture. It is also a distributed system, somewhat. You have a man-machine interface. You have a model, quote-unquote, which is a compute node. There is a communication node, and then there are actuators and sensors. Same basic architecture as any embedded systems. Now, what happens in these systems when something happens? So you got the sensor that takes some information, then they communicate this information, then the compute node takes this information, manipulates it, then through communication sends it to the actuator, and the actuator puts the action on the environment, on the real world. So these phases for an asynchronous model, like for example in automotive there is a CAN network, is an asynchronous model, happens wherever, right? So something, a sensor puts up a data, and then everything starts, right? Communication, computation, actuation. Another thing happens, it may be almost immediately after, everything starts, boom, 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 boom. And then there is a chance that everything kind of collides, right? So now, what is the goal of the synchronous paradigm? The synchronous paradigm is to have the computation and the communication occur in non-overlapping phases. So if there are not overlapping phases, then you can put order in this gigantic mess. So you are going to have a cycle where all the sensors tell the rest of the world what they are doing, and then the communication takes place, so it gets distributed to whoever needs to know. Then the computation occurs. Then when the computation is finished, then you have a communication phase where this information that the model has been able to compute to be delivered to the actuators. So how are we going to make this thing work in the actual physical system? So we know what is the tricks in the synchronous design, which is the clock and the register. How are we going to do this in a distributed system? So that's the goal here. So the problem is design the distributed system so that the information from the sensors to the model are accurate and timely. The results of the computation are delivered to the actuators accurately and in time. And if more sensor compute nodes and actuators are present, all the communication are reliable. So we don't have a situation where there is a collision between a variety of information so that the action are going to be a real mess. Okay. So time trigger architecture, what is it? So is a platform for the design of safety critical systems. And functionally, what it does essentially is that the communication is taken care through a TDMA scheme. Now, TDMA is time division multiple access. What does that mean? Is something that is being known in communication, standard communication. And essentially it says that in a round cycle, in a round of information of scheduling of the system, every single node has its own reserve slot. So there is a period in which only one of these guys does something. And then you move to the next one, and this guy does something. Then you move to the next one, this guy does something. Then you move to the next one, this guy does something. And then you start again, right? So this is a TDMA cycle. Now, what is the advantage of TDMA? It is a time trigger model, so it's kind of a synchronous idea. And the point is that you don't want to have overlapping between different guys telling the system what is going on. Okay, so this is TDMA. Okay. Now, notice that the TDMA method of communication is also very much used today in cellular networks. So, that's something that is used everywhere. So time trigger serial bus, but bus in our concept of a distributed system is a quote-unquote bus. We'll see different architectures that are going to be connected with the TDMA model. Now, it's important because we have safety critical things, and so the requirements that are in general placed on this network is that you have a failure probability below 10 to the minus 10 failures per hour for 10 hours, and maximum outage of these few faults that may occur has to be less than 10 milliseconds. I mean, geez, right? So you can be fairly safe if you are running on top of an airplane that the guy doesn't go down, right? These are requirements that come from real safety critical systems. So you got to be able to guarantee this kind of situation. We say before the bus is actually a generic term. So what you see here is a TTP in a single channel topology, which means that all the boxes are connected to buses. But remember that the mechanism of communication, the protocol of communication on the bus is TDMA. Now, most of the buses today are really asynchronous. So whichever guy wants to put some information in, he puts it in and then he sends it out, and hallelujah, let's hope that everything works fine. So in some sense, the time trigger protocol, which is a way of enforcing the time trigger architecture, is a layer on top of the physical layer, which are, in this particular case, the buses. Now, what you see there is a so-called cascaded star topology, in which the communication occurs between the TTP and the star and another star. So in some sense, is a distributed concentrators architecture, right? So this is particularly true when you have a bunch of sensors, intelligent sensors, that connect to a sort of a gateway. When the gateway talk to each other and do the computation, then they send it to the actuators. Now, what you see on the right is yet another topology that people implement, and it is a mixed star and bus architecture. But this is just to say that the actual physical implementation doesn't matter, as long as the protocol of communication is the one that we said before, is TDMA. Okay, now TDMA, as we said before, consists of a cycle of computation, and this cycle of computation is divided into slots, and every slot is assigned to one actor in the system. Okay, and so this is the mechanism of exchanging of information on the network. Okay. Now, conceptually then, the TT time trigger architecture is an integration framework, and so it's a way in which putting together various systems. And we said before that when you put together various systems, your goal is that the whole thing works correctly. Okay, so that's the key point. That the framework is invisible to the interaction of compliant components, so you can do independent design. Remember, one of the goals is to have the tier 1 suppliers to do their own design in such a way that when you integrate, you maintain the properties of a single component. And so that is this architecture. It guarantees that this is the case. Now, integrated modular avionics is a way in which today, for example, Airbuses and Boeing airplanes are designed. And it's called integrated modular avionics just because of this composability issue. And in fact, the backbone uses this time trigger architecture. Okay? All right. So we said before, TTA topologies is you have these TTP nodes connected to the bus. And so interfacing to the bus, so the way in which the nodes talk to the communication structure is critical and does define the TTA concept. So you got this thing that communicates through the TDMA method, but then we have to say how each of a single block interfaces to that TDMA protocol. So what does it do when it writes into the bus, right? And so this is exactly the same as when you have in synchronous circuits. What happens when you have a block, right? And so you compute, and then you write onto a register. And when the clock comes in, you shift this information to another register, right? And then this register is free to have another writing, and this register is ready to be read by the rest of the thing. So we have to do something exactly the same. Right? We have to try to do the same, right, in a distributed environment. So the first thing that you have to think about is that if indeed time is what keeps things in order, what is the most important point when it comes to interfacing this node to the bus is the notion of time, right? And so everybody has to have the same notion of time. So if for him is 8 o'clock, it has to be 8 o'clock for me as well. Because if for me it's 7:59 and I'm supposed to write at 8 o'clock, I say I'm not ready to write, right? But he's ready to read, so everything goes bananas, right? And so we are back to the asynchronous mode of computation. So the shared notion of time is crucial. Now, in chips, I think that all of you know, the ones who know a little bit about circuit, that one of the most difficult things in design today for Intel-like components is clock synchronization, which is exactly the same thing as I'm telling you in distributed systems. So that every block in the circuit is going to receive the same click at the same time, whereas same time means absolutely the same time, right? It has to be the same. Now, on a chip is a small thing, right? And so the delays and synchronization issues seem to be not so grave, but they are still serious. So serious that clock synchronization has its own circuitry to make sure that the clock coincides. So think about, you have this small of a thing and you have problem. Imagine in a distributed system, on a plane, right? A plane is meters and meters long, right? The big planes are 20, 100 meters long, right? And so it's very difficult to maintain the same notion of time. So clock synchronization is the key issue. So in TTP, there is a particular way in which you keep the clock synchronized. And so there are special chips that companies sell that do this synchronization of the various parts. But it's more difficult than what you have in chips. So one way of doing this is that, does it matter if everybody agrees it's 8 o'clock? Or is more important that when he says now, I say now? So it doesn't matter 8, but we kind of are aligned, right? So we say that it's time for both of us to do something together. So which one of the two? The second, right? That's the most important, is that we have to agree. So one way in which you can achieve clock synchronization is the fact that there is an external observer that looks, right? And then he says, well, gee, this guy is off in absolute terms with respect to this guy by so much, by, I don't know, say 10 microseconds, right? And so what I will do then is that I will try to realign these two guys, right? And so, but there are 10 such guys, and everyone is going to have a different kind of situation. So the clock are all kind of disaligned. The notion of time for every block is kind of not quite the same. So what I will do then is that I will decide, I'm the outside boss, and I'm going to say that I'm going to synchronize on the central point. So I'm taking all your notion of time, going to average them out, and I say, guys, the real time is this one. Everybody lines up on this. Okay? So every so many cycles, I have to do this. I have to control that the drift of the clocks are not too strong. By the way, if you want to do some research on this topic, there is yet another protocol, which is called loosely time trigger architecture, in which you are allowing drift of clocks, and you're still fine. Okay? And so this is quite interesting if someone is masochistic enough that wants to read these papers that are quite difficult because there is a lot of mathematics underlining. Holler, I'll send you such papers. Okay. So is that treatment of physical time as first-order quantity is key, as we said. You need to have everybody that think the same about time. Now, by the way, provides fault-tolerant global time base. Fault-tolerant meaning that even if the clock drifts, I have a way of realigning them. And one such scheme is what I told you. And uses global time to specify the interfaces to the bus. Because essentially, when time comes, I will need to transfer the data that I computed to the bus. So how am I going to do that? I'm going to use the same mechanism as in circuits, right? I'm going to have a buffer where I write, and then I transfer this writing into the reading buffer, and the reading buffer is what sends out the data. Okay? So this is the way in which I'm going to do that. The global time, again, uses specified interfaces between nodes, and communication and agreement protocols are the key issues, right? So how you work on this. So you see here is the middle arrow, is the communication network, and that doesn't have to be a bus, can be anything, but we simplify it with a single line. So in fact, it's a communication part. And then you have a host. The host is the node that does the computation or the measuring or the actuation. And then the CC is a communication controller that is this thing, right, that takes the data from the computation, sends them on the bus. So it controls that access to the communication network, right? And so we saw already that one way of doing it is to split it in two, having a buffer where you write and a buffer where you read. Okay. So, all right. So the TTA architecture then consists of the set of electronic modules that are connected to a channel, the interconnection network. The communication is performed using a TDMA scheme. Each electronic module is called a node of a TTP network, and a node consists of a host subsystem and a communication subsystem, right, which is what controls the delivery of the data from the node to the network. Now, communication subsystem consists of communication controller and communication interfaces. Communication controller is when it says go, and the communication interface is where you put the data so that it can be packetized and sent. So the communication subsystem decides autonomously when to transmit a message and whether a particular message is relevant to a node or not. So because what I do is that I post the data on the bus, and then on the communication network, and then the receiving node has to realize if that message is for him or not. So together with the data, I have to also to send who should be interested in the data I'm going to send. Right? So the address, call it. Right? So when the node looks, this is good, reads it, right? And does something to it. If it says, well, my name is not on the address list, so I do nothing. Okay. So again, the notion of the temporal accuracy of real-time data is key. And so the issue is that when you decide, for example, on the TDMA schedule, you have to make sure that the schedule, the round of information, is short enough so that the data that I'm working with are not stale. Because it may very well happen that he is sensing something, for example, the engine is on fire, right? Then he sends this data on his lot. Then you go, and then finally, this information, the engine is on fire, gets to be sent, right? So you want that this is not too late for you to blow up with the car, right? So you have to keep the boundary very clearly aligned. So the decision on the slot to give him, her, and so on, is one decision, and the second decision, how long is the entire cycle. So you have to decide these two things. And so the design, for example, of a good TDMA TTP network is to decide these two parameters. So the window and the slot. And it's a very interesting mathematical problem, by the way. This is what I just said. Real time loses its value because if you look at the content of this register that I was talking about, is what resulted from the computation, and they are sitting there. So that is an image of what is going on in the system. The real information about what is going on in the system has passed, right? So because it does other things in the meantime. And so we have to make sure that what is the image that I'm going to send it out and work on, and what is the real state of the system is not too distant. Okay. So this is a real-time entity, changes its state as a function of time. If we freeze time, that is the situation, snapshot of the system. Now, the information about the state of an RT entity at a particular instant is captured by an observation. So I am observing the system, looking at what it's doing. That is the equivalent of freezing time and say, okay, here is the status of the system in its globality. The real-time image is what I think it is the state of the system, but is somewhat delayed by the fact that we use that particular protocol, right? And so the image and the status, the real status, have to be very close, because if they are not close, disaster occurs, as we said before. So the validity of an RT image is time-dependent, and is likely to be invalidated by the time. So if you have a window that's too long, of course the data are becoming stale, and then you are not providing the right information that you need to operate upon. So an interface is a boundary between two subsystems, and so the memory element is that buffer that I was talking about before. That is where you write things and you read things. And it contains valid RT images of the entities, or real-time entities. We saw before that we have to make sure that what I write on the buffer is a faithful representation of what is happening inside the system, right? So it's a dual-ported memory in some sense, where on one side you have a real-time status, and the other side is a real-time image, right, that you deliver to the network. And so the information-consuming subsystem reads this temporary accurate information whenever is needed. Now, this temporary accurate has to be part of the design requirements, because that will determine the length of the cycle. The communication subsystem then connects the interfaces, obviously, and transports data elements from one interface to another, right? So it's what interfaces to the communication network. So this is a sender, sends the data here, then gets sent. And then there is a writing phase in which the information for that particular node gets written into the appropriate slot for the node to read. These points in time when messages are sent and delivered are written in a particular table, right? Because it is what gives the operation of the interconnection network. And so the contents of these dispatching tables have to be decided. It's part of the design, as we said. How many bits you are going to have and what these bits contain, right? So you divided them in fields. One field is the address. The other field is the payload, meaning the information. So the host computer, so the host subsystem, is an encapsulated computational machine. Encapsulated by what? By the interface. So the interface acts as a detachment from the communication thing. So the host computer, what does it do? Reads the input data in the buffer that is written after the communication phase is done, and writes the output data into another piece of the memory that then will get sent out. So you have these two buffers, as I told you before, one in which you read and one in which you write. So the priori are instances where the input data to the host computer are actually delivered to the interface. And when the output data from the host computer are fetched from the interface. So you write and read at this priori time. Of course, if a host computer has to react to a specific state change, so an event that has occurred, for example, in the sensor, so you read something new, then what does it do? It has to periodically sample the interface, right? So, and that period is the TDMA period, right? So it has to look at this input buffer and trigger some action if indeed that data that is contained in his read interface contains something that tells you do something, right? Sometimes the data are irrelevant and they are left there and you don't do anything with them and you overwrite them. But if it contains some important information, you wake up and do the appropriate operation. Now, the transducer then is what takes, again, this information about the real-time status of the system and delivers it to the rest of the world. So, again, the transducer are introduced to model the input-output system of a real-time system. Okay? So, it is real-time, but it is not, right? So, the important thing is that there is always a sort of a delay, which is given by this clocking mechanism that I was telling you before. But indeed, if that clocking time is designed correctly, it is an approximation that is very close to what really goes on into the system. Now, by the way, you may see in some in drones, right? So these autonomous driving airplanes. You have two models of, for example, of sensors. One is called the push mode, and the other one is the pull mode. The push mode corresponds to the fact that the sensor sees something, and then say, I need to push this, so it's intelligent. So it has to say, this is really something that I need to send out, right? So it is then pushing the data onto the system. The pull is when you have this sampling mechanism, in which the computer says, okay, what are you reading? What is your last reading? And then the sensor communicates the last reading. So the push model is in general asynchronous, and the pull model is the synchronous operation, right? So if you look at most of the autonomous flying system is based on the pull models for all these reasons that we said before. Okay, so similar thing as the TTP architecture. So this one is the way in which a processor looks like. There is an input-output subsystem that we talked about before. Then there is a communication node interface, and then there is a host processor with memory, operating system, and application software. Then there is another communication network interface, and you have a TTT communication controller that delivers the information to the network, that is the one which is based on TDMA. So a standard nodes then consists of two subsystems, a host computer and a time trigger communication protocol, that is that we saw there. And that information that is stored in the communication controller is an internal data structure that is called the message descriptor list. And the message descriptor list is describing what are the systems that you need to communicate to. Okay. So we said before, the host computer is the host computer in the TT model. It is a self-contained computer, meaning that it has its own memory, its own computation, and its own I/O subsystem. And it interfaces with a communication backplane through a communication network interface, which is called CNI. So the CNI is the concrete implementation of the mechanism of communication that we described before. So we say as important point, in fact, that's the reason why it's called time trigger, is the role of time. So time is really what determines everything. And so, in fact, we had a very long conversation with Herman Koppitz and with Edward Lee and others, and where we were trying to really define what is a good synchronization mechanism. And Herman always said, well, we have time, physical time. Why don't we use physical time to do that? And that's fine, except that even if he says that he's using physical time, it really doesn't, right? because it does this chopping, right? So it's really logical time, okay? And in fact, we know that logical time is an essential concept in synchronous mechanism, right? But the way in which you read the paper that Hermann Koppes wrote, who is the originator of this TTP architecture, TTA architecture, he says, let's use physical time as a synchronization mechanism, okay? Which is kind of right and kind of not right. But, that was the original idea, was based on the Newtonian physics. So it's not relativistic time, of course, right? Because relativistic time says that you cannot ever synchronize two clocks, right? So that's Einstein discovery, call it, right? And so you have to think in Newtonian physics in which time can be synchronized, right? So, but in modern physics, that's not the case. But who cares, right, again? Because if we have a mechanism of slotting time, and we have mechanism of aligning reactions, then who cares if you have real time or it is Einsteinian time, right? And that is the notion of logical time, right? Because it's a logical operation that follows through. So in some sense, again, that's the reason why I always kind of debate with the people who are talking about, physical time when they talk about synchronous mechanism, because they are really telling a lie. It's not true that you use physical time. It is convenient to think in terms of physical time because most of the people think of physical time in a natural way. But it's not so, right? Okay. So a duration is a section of a timeline which are delimited by two instants. An happening that occurs at an instant is called an event, of course, right? So an observation of a state of a world is thus an event. So I can call an event my snapshot of reality. So click, this is my reality. That is an event that I'm going to transfer to the communication subnetwork. So how do I timestamp a particular event, right? In this model, in which, again, we are talking about these boundaries, right, that are given by the mechanism of computation and communication, right? So now we say that we timestamp by assigning the state of a node local global time to the event immediately after the event occurrence. So what you do is that you are essentially assigning the real time to the clock, right, when the clock comes in. And so once more, it is physical time, but it is not, because you are pushing the timestamp to the boundary of the interval that you are working with. Then a fault-tolerant internal clock synchronization algorithm establishes the notion of global time. Is what I was talking about before when we said if these two guys have a clock that doesn't quite match, we try to find the intermediate closest time to the two, and then we align the two to that. Right? That's a synchronization mechanism. It's not the only one, mind you. There are all kinds of other synchronization mechanisms. One of your project item is about studying these clock synchronization issues, right? And so you will see that this just one. There are many other ways of doing clock synchronization. So the access to the bus is controlled by cyclic time division multiple access that is derived from the global notion of time. And again, every active electronic module owns a slot, so it's its own. So nobody can interfere in which he does his computation. After a TDMA round is completed, the next TDMA round starts again. And so, in fact, this way of thinking about communication and computation is called a cyclic schedule. So everybody gets his own time, and that is fixed forever within the interval of time that is dedicated to the round of pulling of the various nodes. So the number of different TDMA rounds determines the length of the cluster cycle. So if you have a number of nodes that talk to each other and all of that, then if I want to have yet another hierarchical notion, I can talk about the cluster of nodes that talk to each other with the TTP scheme, but then there is yet another network at higher level of a hierarchy, and you want to use TTP again, then you have to think about the entire round of the internal nodes as being one slot in the TTP at the higher level of the hierarchy. So we said before, the message frames contains different information. So there are n frames, which contains user data, and I frames, that are system messages that are needed for reconfiguration. So sometimes you need to reconfigure. Why? Because maybe some of the nodes is dead, and so you want to cut it out. And you want possibly to redistribute that function to other nodes in the network, so that you are not only, how to say, fault aware, but you're also fault tolerant. So something goes wrong, and you have a way of fixing that problem that has occurred. So the time trigger communication protocol, that is the one that we just talked about before, in the sense of how you agree on the interface, is the mechanism that provides the clock synchronization service, right? And the TTP communication controller must contain different information, its own data structure, but also the message descriptor list, which specify the global interaction pattern between the various nodes, which means the information about the address of the various nodes that are going to receive this information. The temporal and value parameters of a communication network interfaces, which essentially says what is contained in the communication buffers. Now, there are two different ways in which TTP has been implemented. One is called the TTP-A, where A stands for simple, if you like, and it is done for very simple sensor nodes. Now, we are not going to describe that. You can find it in the literature, because it's really a poor man version of the TTP architecture. And the TTP-C, which is the real TTP, as it is being sold. So the TTP-C communication is organized in TDMA rounds, as depicted in the figure that we showed before. And a TDMA round is divided into slots, and each node of a communication system has its sending slot and must send these frames relative to the data and the reconfiguration information. Then the frame size is allocated to the various messages. It can go from 2 bits all the way to 240 bits, according to the different use that you have of this network. And so this frame, in general, contains several messages that have state information and the medal information. So in different rounds, different messages can be transmitted. It's not always true that the same message can be sent. So sometimes you want to package the message in a different way. So this one is the TDMA round, as we said before. And you have, in each TDMA round, you have a node A that has, you see the medal is written in the first part, where you say that the particular node A is sending message M1, M2, M3. Then you have other slots for different nodes. And then node A gives information M1, M6, M8. Then it goes on, and then in node A, again, post M1, M2, and so on and so forth, right? So this one is a repeating TDMA cycle information and writing on the bus. And the cluster cycle is when a certain number of cycles have been taken by the various nodes in the sub-network that you are considering. Now, what about the fault mechanism? So how can you detect if someone is broken, right? So, well, let's assume two different fault mechanisms. And one is the one that is most preferred in this kind of application, is the fault silent model. What is the fault silent mode? Means that if he is broken, he's not going to say anything. So it's mute, right? And so it's like you put mute on your communication, your microphone, right? You put on mute. So what happens? How do I detect that he is broken? Well, if I have a supervisor and checks the slot, if the slot is empty, it means something bad has happened to him because he's not responding. Okay, so you have to do something about it, but you realize that there is something that has gone wrong. Another model that can be taken into consideration by this scheme is the so-called bubbling idiot. The bubbling idiot model says that one node keeps on talking all the time and it doesn't stop. It's all the time. And so how you determine that you have a bubbling idiot in your network? If you notice that the guy keeps on writing, right? Even when it is not his time, right? His assigned slot is stepped over, which means something wrong has happened because you determine the slot and you tell the node that he has to communicate everything he needs to communicate in that slot. And so if it oversteps the boundary, it means something went wrong. Okay? So the essential mechanism to have fault tolerance in this TTP architecture is to have an observer that checks either if the slot is empty, so the guy is broken, or if it has data that spill over the slot that is assigned to it. Okay, so these are the two mechanisms that can be done. Now, by the way, there are ways in which you can design the nodes so that if something breaks, they are silent. Okay, so in fact, there is an implication on the people who are doing the modules of the design. Remember that we have this vision that there are companies that are designing the blocks and companies that integrate the blocks, right? So if I'm controlling a car, I want to know if this module is broken or not. And so I will ask the guy who's designing this block, if something breaks inside, you cut every communication, okay? And so you have to design that node in that way, okay? So that's a way in which you can take care of the fault robustness. And why is it robust that way? Because at the moment in which I realize that this node has gone wrong, then I'm going to, in fact, the protocol of TTP is rather complicated because it will allow him to be silent for one cycle. If the next cycle is also silent, then you know it is broken, and so you cut it off, right? Because it may be partially absent because something has temporarily happened. Now, once I determine that he is broken, then I have to reconfigure, right? Because I have to assume that I have a way of replicating the function that he was carrying. And so I have to give this function to somebody else. And so I need to send the reconfiguration message and say, you guys have to reconfigure because you have to take care of this function that is not carried out. Sometimes you have duplication of components. So you have, for example, this node is replicated, and this other node was just doing exactly the same thing as this guy was doing. And so if something has happened, then I shut him off and I go to this other node. So that is the way in which I provide fault robustness, right? So in such a way that I can take care of the fault itself. Another way is that say, okay, guys, it's broken. I have no way in which I can reassign things, and so you better put up a big red flag on the screen of the driver and saying, go slow, stop as soon as you can because there is a serious problem on the thing. Okay. Now, the fact that you are broken or not is expressed with this notion of membership function. So you belong to the round if you are communicating. If you are not communicating, you don't belong. So the membership function is false for that particular node. Now, we said before that this mechanism is indeed allowing a top-down design, which is the part of the concoction of the various subblocks together. And in fact, you partition the system into a set of nearly autonomous components. You specify functionality at a high application-specific level. You specify the timely information flow. So when you need to have the information so that the snapshot of reality and the reality itself is not too far. Then you design the message description list of the communication controllers and determine the point in time when you need to activate the communication. So the first design phase then results in the specification of temporal firewalls, so of these boundaries of the TDMA slots. Then the component design instead is that the components are designed considering the constraints of the architectural design phase. So what is it? The known points in time when information must be delivered are the deadlines of the component. So I have to say to this component, you have to compute your whatever function within this slot. Is what I decided to be your slot. Now then there are two situations. one way that you can do that, so you can compute within that boundary, or you cannot. And then what you have to do, you have to iterate. Right? Now, when you design a microprocessor, this is exactly what you do. So you have a clock, then you try to do the combinational logic in such a way that the propagation time is within that clock. If the propagation time of a signal between register is longer than that, you have to go back and readjust the clock, okay, because it takes longer. Right? And this is exactly the same kind of mechanism here. So there is a bottom-up part, which is the reuse of components. And so the input firewall parameters determine what a designer is supposed to do. So, for example, he can say, look, my computation, this is a bottom-up. So I have a bunch of components. Each one is characterized by its response time. And so he's saying, I can do this computation with this time. I cannot do faster than this. This is my boundary. And so when I do the decision about what should be the overall integration scheme, I have to take into consideration that I cannot give him a slot which is shorter than what he can do. Right? That's the bottom-up part. So when you do the intersection of the top-down and the bottom-up, as I said before, either the two agree or they don't agree, you have to change the top-down design part. So this one is very well along the line of the platform-based design principle that we took at the second class, right? So it seems really that everything that you can do in terms of design reuse and so on can be fit in this domain. Now, I told you that the time-triggered communication, of course, has its own goodness, right? And the goodness is the fact that you are reactive, really reactive. Something happens, you immediately take care of it, right? Now, we say before that if you do that, then you cannot predict the behavior of the system because the way in which the system reacts depends on the data. And so if I give you a particular set of data or an order, the behavior of the system is going to change. Now, in the case of the TTP architecture, is not the case. It's always going along with lots and doing things along this time. So it's deterministic. So you always know what happens. In the time trigger communication scheme, it's very appealing because it's very performing. On the other hand, you don't know what's going to happen, right? So, and that is the sad story. Now, when you get into the communication of your laptop and so on the internet, now most of this communication scheme, actually all of it, is so-called best effort, so which means that the communication is asynchronous. There is no guarantee of anything. Now, in the communication, for example, if you have a wired communication, the way in which, for example, your computer are connected together when you sit on your working table and you have the plug coming into the appropriate plug, most of the time is Ethernet. Right? So Ethernet, what is it? Is a protocol on one side, and it is a physical implementation of the wiring. Right? Now, what is good about Ethernet? That Ethernet now is very cheap. Right? Ethernet controllers are very cheap. It's very well debugged. You know, so how many years? Probably 30 years that we use Ethernet. And it's damn cheap, right? So controllers are really cheap, right? And it's very well performing. We know we can go really very, very fast. Now, the problem with Ethernet, it is an asynchronous protocol, right? And so we have all the issues of non-determinism, this, that, and up and down. Given the fact that you can funnel through a lot of data very, very fast, there are some people who say, who cares if I don't have determinism? Because the network is so fast that no matter what, I'm capable of responding to all the reactions of the system. So I don't have to worry about it. It's immaterial because everything can be taken care of. Now, it's fine as long as you talk about computers. It's fine as long as you talk about toys and robots, but it's not fine if you talk about airplanes and cars, right? So the idea is that, can we combine the two, right? Can we build up a network that has the characteristic of being time-triggered, and yet the physical underlying system is Ethernet? The answer is obviously yes, right? Because I can use it as a physical mechanism, a lower protocol, Ethernet, but on top of it, I'm building something that makes it behave synchronously. Now, this is the direction of the future. Everybody is doing this. Do you have a car? Do you have a plane that works on this concept? Not yet. But every single car company, every single airplane company that I know are thinking about this Ethernet plus asynchronous protocol. Now, one way is to do TT Ethernet. Other ways are the AV Ethernet, which is similar in concept, but is synchronizing Ethernet, right? So that's the future. So we say before that state messages are intrinsic in the notion of synchronous, and event messages are intrinsic in the notion of event-driven communication. So, and an event message contain event information, are queued and consumed, so there must be a queue that you have available at the computing node, so that every time something comes in, it goes into the queue. Every time you have free time, you consume an element in the queue. Okay? Now, of course, this why it is non-deterministic, because this queue has to be finite. Right? I cannot have an infinite queue. And so if by some reason the data come in really fast and I'm slow to react to this data, it so happens at some point something gets dropped or something gets overwritten. And so I don't know. It's non-deterministic. Behavior is who knows, right? And that's one piece of the problem. The state message, as we said before, is time triggered. So whatever I read in the data, that is my message, right? So in the output buffer, that's what it is. And so I don't have to worry about overwriting. I don't have to worry about queues. A two-body buffer is plenty good enough. It's all I need. So no queues, no nothing. Of course, the problem with the state messages is that the state may not be the real state of the system. And so that's the reason why we have to keep the boundaries of the slots close to each other. Now, so the comparison between event trigger and time trigger communication schemes are right there. So event messages are in the event triggered and state messages are in the time triggered. Now, the temporal control is derived from the occurrence, right? And so it is unpredictable because I don't know which data are going to come. I have to look at all possible data streams that can ever appear to decide what is the situation. Now, on the other hand, in the time trigger, the temporal control is derived from the progression of time, and so it's predictable. Right? That is the determining factor. The event trigger, the nice thing is that it's flexible because whatever can go, just plug in a component and everything continues to work. But on the other hand, the time trigger information is about interoperability, so that the information can be exchanged in a controlled way. You have large jitter in event trigger, and of course minimal jitter because you have these boundaries that are slotting the time. And so the maximum jitter you can have is the interval between the two boundaries of the slot of the TTP. In the event trigger, you have no precise temporal specification of the interfaces. On the other hand, in time trigger, you have precise temporal specification. It's very good for sporadic data, the event-driven, but it's very good for regular data if you have a time trigger architecture. The membership, so finding out something is broken is very difficult. On the other hand, in time trigger is easy because of the assumption that you make. You have a probabilistic access to the bus or to the communication network on one case, and you have a perfect determinism given by the replication of the cycles. So these are the trade-offs. Now, there are situations in which one solution is better than the other, and you have situations where one solution, when both of them are not so good. And so how can we do better than each one of them is, of course, putting it together. So Ethernet is an asynchronous mechanism, and so the asynchronous communication, the transmission points in time are not predictable, and in general is used by very high speed. So the unpredictability is covered by the fact that you are so fast that you hope that no overlapping or no contradiction between data is ever going to occur. Now, the motivation for Ethernet, as we said before, is damn low cost, extremely good performance. There are lots of cheap providers that do Ethernet chips. And so the idea is to combine the time trigger architecture with Ethernet. So the lower level is going to be Ethernet, and on top of it is going to be TT. So all messages, the idea to do in the TT Ethernet is to have all messages that are compliant to the Ethernet method, so that the existing tools can be leveraged in both cases, both for the Ethernet and for the time trigger information. So Internet compatibility enables the use of technology that is continuously evolving, is faster and faster, and is cheaper and cheaper. So this is very appealing for every company. And the problem is that, again, it cannot be predicted. So how are we going to combine the two? So you have closed-word communication, which is the synchronous approach, which is high cost because you have to have synchronization of the clock, you have to have controllers of the network, you have to have controllers everywhere. The open word communication is this Ethernet and asynchronous domain, which is certainly low cost but is not trustworthy. And so there is a market, quote-unquote, between the two. Now, these one are slides that are provided by TT Tech, which is a company that sells this idea of combining TT with Ethernet. And as I said, is the one that is dictating the protocols, the IEEE protocols that are going to be adopted as standards in this domain. So that's the reason why I'm showing you these slides, because this is the way of the future. So not only the interest in TT Ethernet is because of the low cost and so on, but also because there are many systems for many large-scale applications in which the criticality of the components are different, or the messages are different. So there are things that are really critical, and you want to deal with them with a time trigger protocol. And there are things that, who cares, right, are sporadic, and doesn't matter if they are really gotten the way in which they're supposed to. And so the idea of mixed criticality system is to have particular locus for these non-critical messages to be communicated asynchronously. So I would like to have an overall synchronous mechanism in which I can take care of non-important messages in, cheap ways. So there are two approaches to take care of this asynchronous information, which is sporadic and is not so important. One was given by a protocol that became very fashionable in the past 5, 6 years in cars. You find this protocol. It's called FlexRay. FlexRay combines these two kind of mechanisms, but in a very constrained way. And FlexRay controllers are even more expensive than the TTP controllers. So there was a time in which these things were included in the cars, but the advent of the TT Ethernet and AV Ethernet is the way of the future. Is much less expensive and much more performing. So that's the way in which we are going to go. So this combination of Ethernet and time trigger protocol has the nice feature that combines several traffic classes. There are time trigger, as we said before, so the kind of things that have to be absolutely safety constrained. There are rate constraints, which means that there is a constraint on the rate in which this data occur, and best effort. And best effort, we said, is a basic mechanism of Internet communication and computer usage. So time trigger level, it dispatches messages according to a predefined communication schedule, as we have seen before. The rate constraints inform minimum duration between 2 frames of the same stream, and best effort is standard Ethernet, right, which is a standard asynchronous communication. So that is the way in which the TT Ethernet packages the messages. And you see that there are in between time triggered windows, there are things that can occur whatever, right? So these slots are assigned to communications that belongs either to the rate constraint or to the best effort model. As you can see, then the time trigger slots are very well assigned, and they always occur in the same way at the same cycle, but all the rest can occur wherever, right? So you can think that there is a layer of application which is sitting on the time trigger extension of Ethernet. So there is a basic protocol. On top of it, there is a protocol which is time trigger. And on top of it, there is all the application layer. So the application layer looks at the TT Ethernet as a set of services, and the services are time trigger communication, rate constraint communication, and asynchronous, full asynchronous communication, or best effort communication. So it's a communication infrastructure when you have the various time trigger Ethernet switches, and you have the various attachment, if you like, that can be anything at all. So you can have parts that are CAN network, for example, for communication of low importance nodes in the network itself. There are, for example, TX, FX slots, which are flex ray slots, and that are safety critical elements. And you have TTP buses that can be attached to it. And so it is an heterogeneous way of combining any kind of protocol you can dream of with the, infrastructure that is extremely well-performing and extremely cheap. So that's the big appeal about TT Ethernet, which can be applied, hence, not only as safety critical, but can be applied to anything in the world, giving variety of different things. And so this is the end of the class about time trigger protocol. So you see it is a synchronous mechanism, but you see all the complications that you need to deal with when you want to implement a synchronous mechanism for distributed systems. So you have to deal with communication, how communication is taking place, TDMA. You have to deal with how the single nodes interface to the TDMA communication. So you have to have this notion of the snapshot of reality or real-time images. And you have to study a way of transferring this data into the TDMA slot, right? So all the combination of all these things then yield a way of implementing a synchronous mechanism onto a physical system which is made of nodes which are connected together by wires can be 10 kilometers long, right? Now, of course, the goal is also to eliminate a lot of these wires and to go down to very few wires. Now, how can you do that? Only if you have very high-performing networks, and so that's the reason why Ethernet is so important, and that's the reason why TT Ethernet is such an important protocol for the future. It is implemented today? Not yet. Excuse me? Well, the time trigger model is essentially using time, is like this notion that time determines the slots, right? So the isochronous model is an abstract model. So the time trigger model is an implementation, right? Isochronous is an abstraction of the communication which occurs at the same time, right? So you can say that the time trigger is a way of implementing isochronous. Because isochronous, as the word says, it happens at the same time, isochronous, right? But that is an abstraction model. Now, the time trigger is a way of making sure that the communication is isochronous, but it is not. In logical time, it is isochronous, but it's not really isochronous. Exactly. And so, again, the implementation man, it has to take care of this issue of the fact that when you slot the time, right, you are doing an approximation, right? And so it's an implementation issue, right? And so the class today was about, again, explaining how that implementation goes. In fact, time trigger architectures, we're talking about architecture and protocols. We're not talking about time trigger models or abstract models, right? You could do that, but it's rather complicated. By the way, all of this can be formally verified. So because it's a synchronous model, the only thing that is almost unverifiable. So there have been people who have formally verified the protocol and the architecture, so you can be sure that there is no error. But the thing that makes really life difficult, can you imagine what it is, the most difficult thing to guarantee? It's not obvious, but so the basic scheme can be formally verified. So all the synchronicity and the time trigger protocol and everything is fine. is the fault tolerance part of it. Because you have lots of assumption about the full model, and then you have to see this membership function, how it works, and so making sure, guaranteeing that if something goes wrong, you can see is very tricky. So there is no formal proof that that is going to happen. Okay, so that is the most difficult part. So you have to deal with simulation or analysis or whatever you want to do. But everything else is formally verified, which makes this thing really robust also for even defense application and the like. So, in fact, most of the defense applications are already TTP since long ago. Okay? Other questions? Okay, call it a day. Yes? No, yeah. There is an announcement. So remember that you have to apply for the regrading, and the deadline is this coming Thursday. No, next Tuesday. Okay. So after that, you are dead. Okay. Bottom line.